Hello, I am Dr. Kyoung-Hee Kim, Professor of Architecture and Director of the Integrated Design Research Lab at UNC Charlotte. In this lecture, I'll be discussing the protect function of sustainable building envelopes, one of the three key themes from Protect, Promote, and Regenerate. In the introductory video, we briefly introduced the overview of sustainable facades. The building's outer shell must first and foremost protect and provide a safe barrier between interior and exterior conditions. For the protect function of building envelopes, the architecture of the well-tempered environment by Reyner Banham is a good reference. Banham argues that buildings are not passive shells, and they are gizmos that actively control the indoor environment. In this view, the enclosure becomes an active system, one that filters, regulates, and maintains conditions. This includes protection in a structural sense, keeping the building standing and secure, as well as environmental protection, shielding us from weather, controlling heat, keeping water out, ensuring safety, and even protecting wildlife. In the Sustainable Facade System introductory video, we discussed three broad categories of functions in depth: protect, promote, and regenerate. In summary, protect refers to the envelope's role in shielding and safeguarding the building and its users. Under protect, we include a range of performance aspects from structural integrity and climate control all the way to safety and environmental protection. The second function, promote, focuses on enhancing the indoor environment and user experience. Once the basic protections are in place, a sustainable envelope promotes good indoor environmental quality and biophilic qualities to support occupant well-being. The third category, regenerate, refers to the envelope's role in actively contributing to the regeneration of resources or producing regenerative effects. From this slide, I will talk about technical details that provide protect functions. The basic types of building envelopes include glazed and opaque building envelopes. Understanding these facade types is important because the strategies for protecting can differ between a glazed enclosure and a solid wall. The images and labels here, numbered 1 through 4 for glazed and lettered A through D for opaque walls, correspond to common facade systems. This slide focuses on 4 glazed envelope types. A storefront is a ground-level glass wall system typically used in retail or lobby areas. A window wall is essentially a cladding system where each floor of the building has a continuous band of windows installed on top of slab spanning slab to slab. These systems are common in residential enclosures and for balcony areas. A curtain wall is the hallmark of many modern high-rises. It is an exterior glass wall that hangs off the building's structure like a curtain. Unlike window walls, curtain wall systems are typically installed from the outside lower levels and hung. A window refers to a punched opening window, the traditional individual window unit set into an opaque wall. We will go over the opaque wall types in the coming slide. Windows play an important role in reducing energy consumption in buildings by contributing to good R-value, unwanted solar control, and daylight transmission. As you can see here, this slide illustrates the components of an insulated glazing unit, IGU, of a window. An IGU is what we often call double pane or triple pane glass. The diagram labels parts of a typical IGU cross-section, including edge of glass, silicon primary sealant, and non-metal spacer sealed with butyl primary sealant. What do these components do for the protect function? In essence, a modern window is engineered for thermal and moisture protection. By sealing 2 panes of glass with an air cavity gap, it protects the interior from heat transfer by keeping conditioned air in and extreme temperatures out. Additionally, high-performance glazing regulates solar heat gain and allows for controlled daylight penetration. By using the right materials at the edges of the window, such as non-metal spacers, we ensure the window unit doesn't become a thermal bridge in the building enclosure's insulation and remains weatherproof over time. This contributes to meeting energy requirements, part of the protect function, and improves both thermal and visual comfort. Let's shift our focus to opaque envelope assemblies. As shown on this slide, key construction components are illustrated from left to right for mass wall, metal wall, steel-framed wall, and wood-framed walls. Unlike glazed systems which deal heavily with glass windows and thin frames, opaque walls involve thicker, layered constructions that support structural loads, insulate against heat loss, and keep water out. A mass wall on the far left is a heavy solid wall. Examples include thick masonry walls, concrete walls, or CMU walls. These rely on the material's mass for both structure and often thermal performance. They can absorb heat and slowly release it, helping with thermal stability. A metal wall refers to cladding systems made of metal panels sandwiched with insulation. The metal cladding can be aluminum composite panels or steel cladding panels. For structural metal systems, the insulation is typically rigid to provide composite action against structural loading. Non-structural metal walls, on the other hand, need to be attached to a supporting frame or backup wall via thermally broken Z-clips. A steel-framed wall is a very common type of opaque wall in commercial and institutional buildings. A steel-framed wall means the primary structure is light-gauge steel studs, such as C-shaped metal studs, typically 16 or 20-gauge steel. These studs receive sheaths, insulation, and exterior finishes. A wood-framed wall on the right is analogous to the steel stud wall, but used in low-rise and residential construction predominantly. Wood studs are typically 2x4 or 2x6 lumber and form the structural frame of the wall construction. They also receive sheathing, insulation, and exterior finishes. The vapor barrier is critical to mitigate condensation within the wall assembly and interior surfaces. As a rule of thumb, the location of the vapor barrier is always on the warmer side of the exterior insulation. This slide shows another example of opaque wall construction. Moving from the interior to exterior, it consists of the structural stud wall, sheathing, batt insulation between the stud walls, exterior continuous insulation, a vapor membrane to the warmer side of the continuous insulation, a waterproofing membrane facing the air cavity, and brick veneer exterior finishes. This assembly provides structural strength and stiffness from the backup stud wall, fire resistance, as well as moisture and air resistance. In an opaque wall assembly like this detail, insulation can be placed both within the stud zones and as continuous exterior insulation or exterior insulation only, depending on wall depth constraints and energy performance requirements. While insulation within the stud cavity is interrupted by thermal bridging at the stud area, exterior continuous insulation covers the entire wall assembly, significantly improving overall thermal performance, enhancing energy efficiency, and reducing the risk of condensation. Vapor barrier generally is on the warm side of the insulation or the side that faces the higher vapor pressure. In cold climates, the warm side is the interior heated space, so often a vapor retarder, like polyethylene membrane or special paint, is placed on the interior side of insulation to stop moisture indoor air from migrating into the cold wall where it could condense. Now let's look at an interface detail between a punched window and the opaque wall assembly. A punched window refers to a window that sits in an opening within an opaque wall, as opposed to an all-glass curtain wall or all-glass window wall that we discussed in the previous slides. This slide shows a cross-section detail of a window installed in a stud wall assembly, highlighting how the window is fitted and how the surrounding wall layers are integrated with the window perimeter. It is important to maintain the continuity of all those important layers such as waterproofing, insulation, vapor barrier, etc. When you put a hole in an opaque wall for a window, you interrupt the wall's layers, and special care is needed to tie the window into the wall's weather and thermal control system. There are a few key aspects to consider at the window-wall interface consisting of 1. Structural support and framing of the opening. 2. Weatherproofing and flashing at the interface perimeters around the window. 3. Air sealing and vapor control. And 4. Thermal continuity, insulation around the window. Ensure that the window opening is not a weak link of insulation and waterproofing within the wall. If done correctly, the window wall interface will be weather-tight, airtight, and well insulated, nearly as good as the continuous wall. Shifting gears, this slide introduces the curtain wall system, a very different approach to building envelopes compared to opaque walls with punched windows, as discussed in the previous slide. A curtain wall is a fully engineered cladding system that is typically all glass, glazed, or a mix of glass and opaque panels assembled within the perimeter metal frames. It hangs on the building structure like a curtain, hence the name. A curtain wall is usually prefabricated or assembled from components, and it forms a continuous external skin across the building's facade. Curtain walls incorporate both transparent vision glass for windows and spandrel sections, which cover areas of floors and structural elements. This slide shows the spandrel zone. The spandrel box is usually opaque with a backpan and insulation, so it hides things like floor slabs, ductwork, or wall partitions from outside view, maintaining the all-glass appeal. The curtain wall's job is simply to separate indoors from outdoors, keeping weather out and comfort in. The key components of a curtain wall system are vertical and horizontal framing members made of aluminum or sometimes steel in heavy-duty designs, and infill panels, which are often glass vision panels or opaque spandrel panels. In this slide, we compare two common methods of installing curtain wall units: top-mounted anchor brackets versus face-mounted anchor brackets. The figures here show the difference in how the anchor bracket attaches to the concrete slab. The top-mounted anchor on the left sits on top of the floor slab. In this configuration, an anchor channel is cast into the top of the concrete near its edge of the slab, and the plate bracket is fastened down into it. The curtain wall mullion comes with pre-installed curtain wall brackets, and the curtain wall brackets sit on the anchor bracket at the top of the concrete edge. This approach is suitable when a spandrel panel bypasses above the slab and raised floors are installed to conceal the top-mounted bracketry. This face-mounted bracket on the right attaches the curtain wall to the vertical face of the slab. Here, the anchor channel is cast into the side of the concrete slab. The Curtainwall bracket then bolts onto that vertical face anchor bracket and carry the mullion. As a rule of thumb in industry, face-mounted, edge-of-slab attachments are preferred when you want full floor-to-floor vision glass, allowing the curtain wall to bypass the slab. This slide illustrates curtain wall installation. A construction worker guides a unitized curtain wall panel as it is lowered into place from above. Each unit is pre-assembled off-site and then hoisted into position for installation, engaging with the panel below in the facade. This method ensures rapid installation and precise alignment on site. I will quickly go through TWA Flight Center Hotel in New York City. This project is a fascinating blend of old and new. TWA Flight Center, the gull-wing terminal, was designed by Eero Saarinen and opened in 1962 at JFK International Airport. It is an icon of modernist aviation architecture. The TWA Flight Center's exterior features a sweeping, wing-shaped concrete shell that evokes a bird in mid-flight. The design is organic and biomorphic and an abstract symbol of flight itself. The project was restored and augmented with 2 new hotel wings, clad in a modern curtain wall system. The TWA Hotel is a prime example of sustainable architecture. With 512 rooms, it targets LEED Gold certification, showcasing innovative design and environmental responsibility. This slide shows interior views from before renovation. An open-plan flowing space unfolds beneath its innovative thin-shell concrete shells. Interior elements also follow the building's curves, such as spiral staircases and mezzanine-level concrete columns. Narrow skylights between the concrete shells bring the sunlight into the space while visually lifting the concrete roof. The expansive storefront glass wall offered travelers sweeping views of jets taking off and landing, connecting the interior with the airport outside. This slide shows a nighttime rendering of the renovated TWA Flight Center. The TWA Flight Center becomes the main entrance lobby to 2 hotel wings that embrace the existing TWA Flight Center, allowing an expressive form to remain prominent. The composition of old and new exemplifies a place of movement and transition, reflecting the building's original identity as a gateway to air travel. This slide shows a plan view of the renovated TWA Flight Center and adjoining hotel wings. The restored flight center now functions as the central hotel lobby, featuring the check-in counters, sunken lounge, Connie Lounge, and connections to a food hall and supper club. The North and South hotel wings, each rising 7 stories, are connected via the original flight tubes. Together, they house a total of 512 guest rooms, about 256 rooms per wing. The layout maximizes natural light and space efficiency, contributing to the building's overall sustainability. This slide shows an exterior view of the hotel building's large, sweeping glass facade, which flanks the historic terminal. These curtain walls are visually striking, highly transparent, reflecting the old terminal's curves, yet they meet modern codes for wind loads at JFK, thermal insulation for energy compliance, acoustic protection against jet noise, and more. Due to the stringent acoustic performance requirements in such a unique airport environment, the curtain wall glazing is made of a 4.5-inch thick assembly consisting of interior IGUs, an air cavity, and an exterior glass panel. This helps with both sound and thermal performance. A thick assembly like this is not standard in most buildings, but near an airport, acoustic protection is key. They likely designed for a high OITC rating to block aircraft noise. This means the system probably includes laminated glass for sound control and safety, a wide airspace, and possibly an inner laminated pane, resulting in the 4.5-inch total glazing thickness. That's quite significant and demonstrates a strong commitment to the protect functions, acoustic and thermal insulation, and impact safety. Since laminated glass doesn't shatter into sharp pieces, it helps protect occupants. As we covered in the previous video under protect functions, this kind of glazing design plays a critical role in performance near airports. The photo on the left shows how the ground-level glass wall meets the site. It features a reveal that makes it appear to float slightly above the ground, introducing a sense of lightness and softening the threshold between the landscape and the building. The expressed mullions add tectonic clarity, breaking down the scale of the sweeping surface while reinforcing its vertical proportions. The photo on the right captures the installation of the curtain wall system. The prefabricated curtain wall units are assembled in a controlled factory environment and then hoisted into place, hung from face-mounted anchor brackets. This off-site prefabrication approach enables faster construction timelines while improving quality control, which in turn enhances performance, weather resistance, and craftsmanship on-site. This slide shows an interior hotel view. Wood paneling and vintage-inspired furniture give space warmth and character. The floor-to-floor curtain wall allows a clear and direct view of the TWA Flight Center. This relationship between interior and exterior captures the spirit of travel, always moving yet tied to place. The interior design of the TWA hotel rooms combines enhanced experience with sustainability. This video was supported by UNC Charlotte in collaboration with the US ASEAN Smart Cities Partnership. For further inquiries, please contact Kyoung-Hee Kim at UNC Charlotte. We look forward to advancing sustainable architecture together.